What's up, guys? So today is Saturday. Went to work and now I'm home. We're gonna do some work today. Today's the 30th. It's 3:15. Code and surprise DTM. Yeah, that's so this is gonna be after that. Okay, let's see, where exactly did I leave off? Don't forget to include card ID key. Put it on this one. I'll change attributes. Okay. Don't forget to ensure that change attribute list is properly depopulated and cleared after sending client object. Okay. That's very important. Move all messages, dirt check timestamp list, and dirt check timestamp order list. Okay. Need to verify item is equal to adder name should only be assigned in receipt section to which send section. Need to modify entire section in line 708 so that dirt check is called one time dynamically as is done for the receive section. I think this is required now that we have made the new DTM changes because each client possesses a particular data point associated with a particular direction. Now with the current version of check calls, we have no way to alter the dir string args. Need to modify so that dirt check is called one time dynamically. I think this is required now that we have made the new DTM change because each client change attribute list and entry consists of a particular data point associated with a particular directory string. And with the current version of dirt check calls, we have no way to alter the. Okay, we have no logic to alter. Okay, true. Yeah, that is true. Just realized that if I'm going to update client change attribute list every time that I update a player game decker, I would probably end up with a circular import issue because client is files. Yes, I could test for see. Okay, so this is where I left off, right here. If I'm going to update, I could test first to see if it would work. I may need to make the change attribute list be a standalone object that can be imported everywhere. Another option would be to append each object's data change. We need to make the change attribute list be a standalone object that can be imported everywhere. Another option would be to append each object's data changes to its associated change attribute and then grab each object's attribute using client change attribute dictionary, appending all the various entries to self before after receiving. And honestly, that seems like that seems like the most do it. Well, because first of all, we already have the logic for this implemented. And it doesn't require any importing. It just requires a simple, you know, like you just are creating a list as a compilation of the other 4 lists or attributes. Call it. Sounds like a good option that makes sense. As soon as you put in a car park. Which object are we going to reference? Okay, so that's where we left off, and so this what we need to do is we need to figure out we can reword this to say determine which option we are going with concerning appends to, or concerning how when changed attribute list concerning how when is populated to avoid circular import issues, logical complexity, etc. Okay, and we'll put this right there. If I update client attribute list every time update player game, we would probably end up with circular import issues because client file imports all these files or parts of them. I could test first to see, if it would work. Check to see if we do see circular imports. Like, I'm pretty positive we would. I don't even think I need to test that. So we stand object can be imported everywhere. So we could say option 1. This would be make the change attribute list be a standalone object that can be imported everywhere. Option number 2 would be append each object's data changes to its associated change attribute current. Well, that's actually not the current logic. And then grab each object's would be to append option 2. Append each object's data changes to associated change attribute along with the concurrent timestamp update value, and then grab each object's attribute, and then have the change attribute grab each object's individual added, appending all the various entries to itself before sending, and after. Well, before sending, if we did that before we sent it, then after receiving, we wouldn't need to do that. So that would just be before, I think. This sounds like a good option. It makes sense. So it avoids reasons this it avoids what? It avoids what? It avoids the possibility of circular import issues. What else? It avoids the possibility of circular import issues. What else? What else does it do? It does more than that. It avoids the possibility of circular import issues. What other issues does it bypass? Let's see. It also allows us to keep relatively the same logic in place, which is avoid complete refactoring of existing system, and a decision and we'll just put this as nice after decision has been made, after concerning which option. Oh my god. Okay. Alright, so now we have structured our things to do. So now we can... First thing, we're going to... do that. Okay, so let's see. Option 1 is make the change attribute list standalone update reported everywhere. Let me think about this for a second. Like, I mean, I don't think there's nothing wrong with doing that. Like, that would technically be cleaner, because then we don't have to like combine, you know, we don't have to combine the four of them into one at a later point, we would just always have the one. And I think I was actually like in favor of option 2, but I don't know if there's any good reason to choose option 2 over 1, because let's see, append each object's data changes to its associated change attribute. Like, that's actually not in place right now. We don't do that. That would happen in dircheck, but we're restructuring dircheck to not work in that way. So I think it would just make more sense, you know, if we're implementing it anyway. Like, why would we use 4 attribute dictionaries and not just use 1? Yeah, so I think that we'll put seems like the better option. I'll put reasons reasons to use this over option number 2. So first of all, it is since we are already having to implement all of the lines which will append each specific data point alteration to the changed attrdict slash changed attribute list, why deal with 4x lists instead of 1? It's more simple, less complicated, less prone to bugs. And more direct. And also skips the step wherein we would combine the 4x dicts into 1x larger dict list. Yeah, so I think that we would actually go with option 1, but I wanted to see, like, could we just say could we just make this could we just leave it as a client object attribute and instance attribute, and then whenever we are dealing with it, like, couldn't we just import only the attribute list from the client file? Or, like, I don't know if that's I just don't think we can do that. I don't think. So let me think about how the logic of this is going to work exactly. So and that raises another question of whenever we are importing this object in the various different locations, which client instance object would we be in? You know what I'm saying? Like, this has got to be client 1 or client 2. So if we were, you know, like how would we know to update a particular attribute list? You know what I mean? How would we know which one we should update? So if we have so if we have each client object having a changed attribute list, let's just say well, we still have to answer that first question, is how would the game know whenever it was modifying data? How would it know which client object to append the data to? Like, so let's think about the different perspectives from which this would happen. So we have the server side. Let's say on the server side we have access to both of those change attribute lists because both of the clients already exist there. So that wouldn't be an issue as far as accessing the attribute lists, and like if we're operating from, if the current client ID is 1, then we would want to obviously update the client 1's change attribute list, etc. But when we're actually modifying the data, like let's say that the data change happens from the progression file. If we're making the change from the progression file, let's say we end up changing the player's hand. Okay, so whenever it enters into the player file to modify that player's hand, the player file has no idea which client object to update the attribute list to reflect that data change from. Let's just say that, well, so if that was a server-side change, we would want both the client 1 and client 2 to reflect this modification. So I suppose that means we would modify, like, would we modify both of the changed attribute lists? You see what I'm saying? Because both of the classes, I mean both of the clients have to receive those modifications. Let's just say that was server side changed attribute list for client 1 and client 2 get updated whenever the main thread alters the player client one's hand, but like I said, we would want both of them to reflect that change. But couldn't we just like couldn't we just send the one attribute list? Couldn't we just update the one attribute list? Like, let's say if we're dealing with player one and player one corresponds to client one, couldn't we just update based on that? Like, one client one, since we're dealing with client one, who is player one, we're gonna modify client one's change attribute list, but we end up sending that changed attribute list to both client 1 and client 2, so that client 2, it's just like the current system, how whenever we make a data change for player 1, it is, even though it corresponds to client 1, since we want client 2 to also visually move that card as well, we would send that data from client 1, server-side client 1, to client-side client 1, but also to client-side client 2. So each client side is receiving data from each client on the server side. You see what I'm saying? So I don't think we would have to update each attribute list. We could just update the one attribute list, and we would pretty much always send out data changes to clients from the server side. So let me put that in the notes. Let's and I'll just put this as notes while brainstorming implementation. Say we could update the changed attribute list associated with whichever client number we are dealing with. We could update the change attribute list that is associated with whichever client object number we are dealing with. P1 hand equals client number 1 change attribute list, etc. We could update, and then what else can we put? With also, how do we make the outer files, player pie, game pie, etc., know which client changed attribute list to update? Essentially, we would determine which player object, game object, we were handling. Game 1, so you'd say actually P1 P1 game, etc., and have that number 1 or 2 correspond to client 1 or 2. And I'm like, so yeah, we already make it so that player 1 is always associated with client 1, and P1 game is associated with client 1, instead of just like it being random. Like, you don't know, maybe you're dealing with P1, maybe you're dealing with client 2 as P1, but we don't work in that way. We have it set up to be aligned. So I'm pretty sure this would be like a solid solution. Since early game logic dictates that 1 is always associated with P1 and P1 game, etc. But what about, but what about files like locations.py, which don't work in terms of 1 or 2? So, and also like the deck, that's another question. Like, so deck which don't work in terms of 1 or 2. Currently, the logic is such that whichever client object thread that detects the changes made to shared objects, such as locate or master deck, is the client object that transmits the changed data to both clients. But this raises the question, like, wait, so what if, well, no, that never happens client side. I was thinking, well, what about when they get changed client side? Because client side doesn't send out to both clients, but the way the project is structured, the game, the objects, like, I think a way to say this, we never actually change the deck object or like the discard pile object on the client side. The only thing that happens client side is the choice. Like, they make a particular choice, which is like a simple Boolean switch, and then based on that choice, that data is transmitted back to the server, and then the server continues progression through the progression file, which is where all of the deck and the discard pile, etc., are modified from. I'm pretty sure that's the way that it works. Yeah, I'm almost certain of that actually. Okay, so and concerning client side, I'm quite sure we never actually modified those shared objects, but rather small Boolean switches are modified client side, and then the Boolean switch data is sent back to the server, where the server continues to modify these shared objects based on those decisions. Meaning that we don't have to worry about the fact that client side changes are not transmitted to both and therefore might not be reflected on the other side. Client-side changes are not transmitted to both clients and therefore might not be reflected to the other side. Okay, so let me think about this. So how are we gonna change this? Or would we, well, yeah, so the way that it works is we have to share this data with both clients. Like if we modify shared object, then that means we're going to modify, like, since we're changing the logic of how this happens, that means we're going to like the current system is going to be overhauled. We're not just going to be checking to see, but like it's not going to be the first one to detect that the changes were made. It just doesn't work like that anymore. The way that it works is immediately when we make the change, we are directly appending the data change to an associated changed attribute dictionary or whatever you want to call it. So that means, like, we have to determine, well, are we gonna append this data to just client 1 and have client 1 be the one to send it to both clients? Are we gonna have it append to client 2's changed attribute dictionary and send it to both client 2 and client 1? Or are we gonna have it be appended to both client 1 and client 2's change attribute list and then be transmitted, you know, to either one of them? I would like to say that we wouldn't have to. I'd like to say we wouldn't have to update both of them, because we could just send one to both. But that makes me like, a little bit concerned about like data synchronization and whatever concerning the fact that that means that client 1 would be more behind in its, like, it would have a lot more data to transfer. It would be sending over all the shared object changes as well as the unshared object changes, and that would clog up the data transfer flow for client 1. I mean, since we have the, well, actually though, that's no, that I don't think that's, is that actually true though? Because well, yeah, because if we're sending the data from client 1 or the thread for client 1 on the server side twice, we're sending it both to the we're sending it to both the client 1 and client 2. That means that client thread is going to be occupied more frequently but I don't know, I don't think that would cause issues. I am concerned about how we would send this data. If we sent all shared object data via client number 1 thread, this would mean that client 1 thread would more often be clogged up with data, with more data flow. The question then is whether or not this would cause bugs. Data transfer issues. If we sent shared object data via both objects, this would mean that client number 1 and client number 2 would have to have special thread logic that would exclude sending the data to both clients, client side, because currently we send out server side data changes from one client's object thread to both client side objects. Yeah, that makes sense. This would suggest to me that sending all objects, all shared object data via, suggests to me that sending all shared object data via client number to this option. Option number 1, and then option number 2. So let's zoom out a little bit. We could update the changes. How do we make the outer files? No. Which Let's determine which players are getting their handling one P2 game, P1 P1 game, etc., and have that number 1 or 2 correspond to client 1 or client 2. Have this be a solid solution to early game logic takes client 1 is always game capable about files like location tech files or 1 or 2. Currently, the object is such that whichever client object thread that the text change is made to shared objects, which is located by state, is the client that transmits the change data to both clients. I'm concerned about how we would send this data. Option 1, if we send all of the shared object data via client 1 thread, this would mean that client 1 thread would more often be clogged up with more data flow. The question then is whether or not this causes bugs or data transfer issues. And I would like to say I don't think it would cause issues because of the system in the delay sorting system we are putting in place. Okay. Yeah, I don't think it would. It would. I mean, the game has still has to wait for input from the clients to progress. It's not like the server is always running, meaning that client 1 would start to fall behind as far as being able to process or keep up with the exchange of data, and that would cause transfer issues. A third option would be to make another thread which handles the shared object data, and this would, I don't know, we would have, but the way that Python works anyway is, from how I understand it, it's never actually multi-threaded. It's that we have multiple threads working at exactly the same time. It's more like everything happens one at a time anyway. But again, I think this is more a question related to the structure of the game and how it progresses. And I think that the way that this game progresses, which pauses until it receives user input client, I don't think this would be something we should have to be concerned about. I think it would work quite well, but you know, I'm not sure about that. I'm trying to talk about this more so that I can be more sure about it. And yeah, so basically I am just 100% sure. I feel like it's I feel like we would be fine. So trying to just think more about it. You know, like there's got to be an issue with that, right? If client 1's doing all the sending. And what about if client 2 is free? How do we know that? How would we know if it's free or busy? That is what if we were waiting on input from client 1, like before we could apply these shared, but it wouldn't. It's like, would that actually be a thing though? Because well, I don't think it should be a thing because everything should be sorted, which means we wouldn't be waiting on the client until we had already applied data that should come before it. So that concern should be out of the window. At least, yeah, I'm thinking it should be out of the window. That should be no issue at all. So yeah, I'm just gonna go ahead and say I think this will be safe, and I'll put option 1. This what seems like the better option, and then I'll put after contemplating, discussing amongst myself, I have determined that this option would almost certainly be safe. And is the choice we should go with. Alright, so I'm gonna take a little bit of my medicine real quick. I'm feeling kind of stuffed up. I'll be right back. Take a little 5-minute break. Oops, I forgot to share my stream. Okay, we're back. I'm trying to find what I was listening to. Something came on when I was at work. I can't. I don't know. It was like an instrumental thing, and it was really good. It wasn't this. Yeah, it wasn't this, because it was like not. There was no words. Um, it was like a playlist. Or I don't know, maybe it wasn't. Anyway, it's no big deal. Whatever. Okay, so back to I'm gonna go till 5, so I'm gonna go 40 more minutes. Oh, so let's try and get something done here. Alright, so we left off right here. What option we should go with, and that is gonna be the option 1, which is okay. If we send all shared object data via the client 1 thread, okay, and that sounds good to me. I feel like we thought about it a good bit, and it also coincides with existing logic. So then we would have to just make it to where whenever those particular objects, the shared objects, are modified, we would always update the client 1 Okay. Yeah. And I was just thinking, I'm like, wait a second, well, if none of this is actually concurrent, then what's the point of having two separate client threads on the server side? Like, if we had one, well, you have to have a thread for each client, right? Because I'm trying to think, like, what makes having two client objects on the server side, two client threads on the server side necessary? Honestly, I'm like, damn, I feel like I have to be wrong about this, but I feel like, as I'm thinking about it right now, it seems like there would only be, like, it wouldn't matter if there was two or if there was one, because we would still be able to send data from each of the client objects. I'm just trying to think of, like, I know that there has to be a requirement, and I should know the answer to this. Why we have to have a thread for each client object on the server side. Because if we don't have an individual thread on the server side for each client, that would mean what? That would mean, like, would data coming from each client not, like, be distinguished? Since we don't actually have concurrency on Python multi-threading because of the global interpreter lock, and that's some I just don't completely understand that. I want to ask Gemini about this and see if she can explain it to me a little better, because I just don't understand it completely. Using Python, do we have to have two separate threads for each corresponding client on the server side? Or could we just have one thread and have the two clients communicate with the one server side thread? So using Python, do we have to have two separate client server side client threads? For each corresponding client on the client side? Or could we just have one thread on the server side and have the two clients on the client side communicate with the one thread on the server side? Let's see if she understands what I'm saying here. If it understands what I'm saying. Okay, you can handle multiple clients with a single server-side thread in Python, but it's crucial to approach it carefully. Here's a breakdown of how it works. Socket creation. The server creates a single socket and listens for incoming connections using socket bind and socket listen. Client connections. when clients try to connect, the server accepts each connection using socket accept. Continuous loop. Rather than creating a new thread for each client, the server enters a continuous loop that checks for incoming data on any of the connected sockets using select.select. When data arrives on a socket, so wait, the server creates a single socket and listens for incoming connections using socket.bind and socket.listen. When clients try to connect, the server accepts each connection using socket accept. Rather than creating a new thread for each client, the server enters a continuous loop that checks for incoming data on any of the connected sockets using select.select. When see, I don't like this noise, like this sound. I like the sound, but I don't like the voices. It distracts me. It's a pain in the ass. Like, there will be no voice, and then for a minute there will just be this guy repeating himself. Process. When data receives socket, reads it using. Oh no, man! Come on, dude. Jeez. When data arrives on a socket, reads it using receive, okay, and then processes the received data as needed, sends any response back to the appropriate client using send. Okay, so let's read the key considerations. Single threaded limitations. While this approach avoids thread overhead, it can limit performance for long blocking operations or CPU intensive tasks. Okay, yeah, that's right, because like when you have two threads, when you're like, let's say we're running a while loop on one thread, the other thread isn't caught up in that blocking operation. It continues to work while the other thread is blocked. Okay, so that makes me remember. Okay, that's why. And then if multiple clients send requests simultaneously, the server might not handle them concurrently, leading to delays. Synchronization. Multiple clients access shared resources. Careful synchronization is crucial, using mechanisms like locks to prevent data corruption. Well, this actually, like, technically would still be an issue that we have, right? Because we do have multiple clients accessing shared resources. I think it's just that the structure of the game and how the data is processed, it allows us to avoid like it just bypasses this security issue by the nature of chance. Like, it's not necessarily that we have it coded to be secure regarding this, it's just that the way the specific data exchange happens in the game, we're not gonna be modifying like P1 hand from one server side thread at the same time we're modifying the P1 hand on the second thread, because if that were the case, well, that would be our race condition issue, and we discussed that before. But I think it's just pretty much the case that that doesn't happen, that we don't ever change the, like, we don't change the other player's data from the other client. We only change, it's like a 1-to-1, 2-to-2 change. If we modify something on client 2's client side, it's gonna be something that's changing either player 2's attributes or player 2 game's attributes. And likewise for the other, we'll call it thread number 1, that is associated with player 1 and player 1 game attribute modifications. So I honestly might need to review this though, because if we're still if we're still having bugs after we finish this data transfer modification, it very well may be the case that they are stemming from rare intermittent race conditions due to this modification of shared resources, because we don't have synchronization or locking. And I'm actually gonna add this as a thing to do, at least as a review, to ensure it's not a problem. So we'll put this as a completely new issue, and I'll call this thread lock sync race condition, and this will be 3:30:24. Review entire review overall game data exchange structure concerning whether or not rare intermittent race conditions may be present due to multi-threaded access modification to shared resources. When reviewing DTM changes, I became concerned that because we did not have any locks or synchronization between server-side threads, this could technically be an issue. I think for the most part this is a non-issue due to the nature of our current data transfer system, which handles, for the most part, I believe, modifying data in such a way that thread 1 corresponds only modifies client data, and likewise for threads number 2 and client 2 data. This still needs to be considered if we encounter these intermittent rare bugs after finishing the DTM as a possible source issue. Needs thorough review after DTM is completely finished. Okay. So we'll just put this after here, and we'll just continue with this. Okay, and then one other thing I wanted to, let's finish reading this. Oh, I thought I finished reading it. Let's see. If multiple clients access shared resources, careful synchronization is crucial using mechanisms like locks to prevent data corruption. When to consider multi-threading. CPU-intensive tasks. If your server needs to perform heavy computations or handle many CPU-bound operations independently for each client, multi-threading can improve performance by distributing work across multiple cores. True concurrency. If you require genuine concurrent execution of client requests, multi-threading allows multiple requests to progress simultaneously. Okay, right. So this allows for faster data exchange. But I thought that Python never truly allowed for true concurrency. But I guess what they mean by that is, like, you can have a measure of concurrency, meaning that while loops blocking on one thread will not block on another thread, but that doesn't mean that two events will happen at exactly the same, like, microsecond, like they would in perhaps like another programming languages like C or C# or whatever. So let's continue reading about this. Alternative to this would be asynchronous I/O, async I/O. Consider using Python's async I/O module for more efficient handling of many concurrent connections without explicit threading. It leverages event loops and coroutines. I don't know what that means. Coroutines. Okay, I see. Consider using Python's async I/O module for more efficient handling of many concurrent connections without explicit threading. It leverages event loops and coroutines to manage I/O operations asynchronously. And I don't necessarily know what it means by I/O. Like, does that mean like while loops, or does that mean like socket socket data transfer processes? I'm not sure exactly. In conclusion, using a single thread for multi-client communication is possible in Python, but be mindful of its limitations and potential synchronization issues. Assess your application-specific needs and performance requirements to determine the most suitable approach, single-threaded, multi-threaded, or asynchronous. For computationally intensive or high concurrence scenarios, multi-threading or asynchronous type can offer better performance scalability. Right. Okay, so now I want to ask about, let's see. Using Python, is there ever true concurrency when you consider the global interpreter lock? No, due to the global interpreter lock in Python's CPython implementation, there's no true concurrency of Python bytecode execution at the process level. Here's why. GIL enforces serialization. The GIL acts as a mutex mutual exclusion lock. It ensures only one thread can execute Python bytecode within the interpreter at a time. This means other threads attempting to execute Python code will be blocked until the holding thread releases the global interpreter lock. What can be concurrent, but with limitations? I/O operations. While Python bytecode execution is serialized, I/O operations like waiting for network data or reading from a file can happen concurrently using non-blocking I/O mechanisms. Threads can be waiting for I/O operations to complete without blocking the global interpreter lock. So a thread can be blocking, like with a while loop or whatever, but that doesn't mean it's actually blocking the global interpreter lock, which means you can have a measure of concurrency, or something like that. GIL release and acquisition. The GIL is released periodically, allowing other threads a chance to acquire it and potentially execute short bursts of Python bytecode. Create the illusion of concurrency for short-running tasks that frequently release the GIL. And I guess that's like while loops. Like a while loop will give it opportunity. Like it's the GIL is going really fast between each thread. So impact on multi-threading. Limited benefits for CPU-bound tasks. Since only one thread can execute Python code at a time due to the GIL, multi-threading offers limited benefits for CPU-bound tasks. All threads will be competing for the GIL, and the advantage of having multiple cores might not be fully realized. Alternatives for concurrency. Multiprocessing. If your application involves tasks that can be truly independent, not requiring shared memory or communication, consider using Python's multiprocessing module. It allows you to spawn separate processes, each with its own Python interpreter and global interpreter lock, enabling true parallel execution on multi-core systems. So yeah, I remember going over this, whether or not I should use multi-threading or multi-processing, but I think multi-threading ended up being said to be the better option for what I was doing, because I can't remember exactly why, but I remember, like, I didn't just pick one based on the flip of a coin. Asynchronous programming. Async I/O is asynchronous programming. Async I/O. For I/O-bound tasks, asynchronous programming with the async I/O module can be a good approach. It allows efficient handling of many concurrent connections or I/O operations without relying on explicit multi-threading. So wait, async I/O. Asynchronous programming with the async I/O module can be a good approach. It allows efficient handling of many concurrent connections or I/O operations without relying on explicit multi-threading. In essence, the GIL enforces a single-threaded execution model for Python bytecode within a process. In essence, the GIL enforces a single-threaded execution model for Python bytecode within a process. However, I/O operations and strategic use of the GIL's release and acquisition can create a semblance of concurrency in certain scenarios. The application every does multi-bit knows about true parallel execution. So now I just want to ask, when using Python, when should I choose multi-threading over multi-processing or async I/O? choosing the right approach for concurrency pattern depends on the nature of your task and desired outcome. Here's a breakdown of when you consider multi-threading. Suitable tasks with a mix of CPU bound and IO bound operations. And I would say that is my case, because I have like while loops and stuff, and I would say that's CPU bound, I think. And then IO is for like data transfer, I think. And then it's good for tasks that benefit from occasional parallel execution but don't require heavy computation. Useful for leveraging multiple CPU cores for tasks that can be divided into smaller thread-safe subtasks. Advantages: simpler to implement compared to multiprocessing. Simpler to implement compared to multiprocessing. Simpler to implement compared to multiprocessing. Shares memory space with the main process, enabling easier communication and data exchange between threads. Okay, I don't know exactly what that means. So multiprocessing doesn't share memory space. Like that means if we, instead of using multi-threading, we used multiprocessing, we wouldn't be able to have like a modification of the same object and then like each thread would have the updated version of that object at its hands. It would instead need to like be told how that object has been altered, which would be like a lot more work to be done, I think. Disadvantages: limited benefits for purely CPU bound tasks due to the global interpreter lock, requires careful synchronization mechanisms locked to prevent data race conditions when accessing shared resources. So yeah, that, like when you're using multiprocessing, you don't have race conditions, I guess, because you're not truly updating the same object. You have like the two versions of the object, and then you would have to like determine some way which object's like data is the most up to date or whatever and all that. At least like that's how I'm understanding it so far. And multiprocessing use cases ideal for CPU bound tasks that can be completely independent and don't require shared memory access. Ideal for CPU bound tasks that can be completely independent and don't require shared memory access. So this would be like, I don't really know of any instance in my game where it would be like, I can't think of anything that would benefit from this. I can imagine, I think, a scenario where it would be useful, like if you had some sort of computation that would, you know, always have to be running in the background for whatever reason. You could put that on its own process to allow the processing of all of the events to be faster by using another. Like you'd, I guess when you do another process, that allows all of your cores to work on that process whenever they're free, meaning that it's opposed to a thread which uses a single core to operate itself. I don't know if that's true. Does multi-threading mean that only one CPU thread will process it, or will it use all threads? That's the next question I want to ask. Does multi-threading mean that each thread is handled by one CPU core, or does more than one CPU core handle each thread's data processing? So let's keep reading this. Use case idea for CPU and suitable scenarios where you want to take full advantage of multiple cores for parallel execution. Separate processes. This means a process means actually anyway. I'm still confused about that exactly. Advantages: enables true concurrency by utilizing multiple cores for independent processes, overcoming the GIL limitation. No GIL restriction allowing multiple processes to be execute Python bytecode concurrently. Disadvantages: more complex to implement compared to multi-threading due to overhead of process creation and communication. Communication between processes requires explicit mechanisms like queues or pipes, adding complexity. Communication between processes requires explicit mechanisms like queues or pipes. Async I/O use cases perfect for I/O bound tasks that involve waiting for external events like network requests, file, I/O, or user input. Well suited for applications handling many concurrent connections or asynchronous operations. Disadvantages: efficiently handles numerous concurrent connections or I/O operations without overhead of multiple threads. Avoids the GIL limitation for I/O bound tasks, improving performance on single core systems. Might require a different coding style compared to traditional threading on multi-processing. Debugging asynchronous code can be more challenging than traditional approaches. Okay. In conclusion, for tasks heavily reliant on I/O operations, async I/O is generally the best choice. Okay, this is the last question I think I'm going to ask, and I'm going to go ahead and quit for the day. Does multi-threading mean that each thread is handled by one CPU core, or does more than one CPU core handle each thread's data processing? In multi-threading, the concept of thread-to-core mapping isn't a one-to-one relationship. Here's how it works. Threads and cores. A thread is a unit of execution within a process. It represents a single flow of control within a program. The CPU core is a physical hardware unit that executes instructions. Multi-threading and core utilization. One core, many threads. A single CPU core can handle multiple threads at any given time. This is achieved through context switching. The operation system rapidly switches between threads, giving each thread a short time slice to execute instructions on the core. One core, many threads. A single CPU core can handle multiple threads at any given time. This is achieved through context switching. The operation system rapidly switches between threads, giving each thread a short time slice to execute instructions on the core. Multiple cores, many threads. If your system has multiple cores, the operating system can distribute threads across these cores for parallel execution. This allows multiple threads to run instructions concurrently, potentially improving performance. Okay. Context switching and performance. Context switching between threads incurs some overhead. The operating system needs to save the state of the currently running thread and load the state of the thread that will be taken over the core. While multiple threads can improve performance by utilizing multiple cores, Excessive thread creation can lead to diminishing returns. The overhead of context switching can outweigh the benefits of parallelism if you have too many threads. Thread scheduling. The operating system ultimately decides how threads are scheduled to run on cores. Scheduling can be influenced by factors like thread priority and I/O wait times. In conclusion, multi-threading doesn't require guarantee a one-to-one mapping between threads and cores. A single core can manage multiple threads through context switching, and through multiple cores can handle multiple threads in parallel executions. The effectiveness of multi-threading depends on various factors like the number of cores, nature of your tasks, and the overhead of context switching. Very complicated stuff here, but I think we have the right choice. Like, I already knew that, but I feel like I needed a refresher because I was doubting. I was like, oh, did I actually make the right choice on a foundational level with this entire project? Which, yeah, I'm pretty sure we did. We probably could have done it either of the 3 ways, but I think this was the best way, and this was the way recommended by like Tech with Tim, which is where I got the skeleton version of how the network was going to be structured and everything, and the data transfer system was going to be structured. I got that from him. So this was 3:15 to 5, so that's 1.75 hours. We didn't get a lot done, but we got some done, you know. It's pretty good for our short little session. So when I pick up next time, I'll be that much further ahead. We'll just say worked, well, actually until 4:30, and then we ask Gemini some questions. So then from 4:31 to 5 o'clock, or 4:55, asked Gemini questions about multi-threading, multi-processing, async, IO, etc. As a refresher to ensure we made the correct choice at a foundational project level. Alright, and then 4:55 to 5, say worked or continued on brainstorming final version of a current DTM focus, which was implementing client.changed attribute list and method of method timing, or method and source of appends to this important object. Mostly determined the final state of actual code implementation. Yeah, and that's pretty much it. And then we staged, committed, and pushed changes to remote repo, and created a new local backup copy of the entire project. Alright, so now we're going to copy this. We'll go back to things to do, and I'll put files I gotta don't work in terms of 1 or 2. Ready to make new files. I'll put 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Stopped here. And this is gonna be 3, 30, 24. Stopped here. Alright. Um, next we need to actually implement all of this code after final decision review. Alright. This actually should go all the way up here, I think. Review this entire section below. Section before adding code. And I made a badass casserole. Time to eat some casserole, dude. Alright, so I'm kind of happy with what we did today. It's pretty good. So first we're going to stage our changes. We're going to go to the root directory. We're going to get branch, make sure we're on the right branch. If we're on secondary, that's good. We're going to get add dot, which adds everything or stages everything. We already have our commit message copied. We don't have any quotations within it, so we're good to go ahead and close it and commit the changes. We create our new commit. It shows the correct devlog message. 2 files changed, 48 insertions, 12 deletions. Now we can go ahead and get push to Canasta secondary, and that's going to push to our remote repository associated with this branch, and it successfully did that. Now we are going to go over to, we're going to close out of this. We're going to open up our folder which contains the project. We're going to enter into it. We're going to copy this Canasta file. We're going to enter into here. We're going to delete this copy, which is from yesterday or day before yesterday. Now we're going to paste. Okay, there it goes. Pasting the new version of the project. We're going to go in and check it to make sure that the devlog shows today, so we know it's correct. 3:30, so the date's correct. We know we're good to go here. So now we have a new backup of this project. We can go back over here and change the date to 3:30 to correspond to today, which is the date of the last backup. There, now we're good to go. I'll see